Hello everyone, hope you all doing well. My name is Panda, and in this video we're going to talk about chapter 2 of the book Machine Learning Design Patterns. This chapter will be exciting because it introduces the first 4 patterns out of the 30 covered in the book, which is exactly what we are here for. But before we dive into these patterns, there are some concepts that the book reviews, which we will also need to understand to discuss the patterns in this chapter. The chapter covers 3 main points. The first being the representation of data, which is actually the title of the chapter, Data Representation Design Patterns. It then goes on to discuss 2 other topics related to data representation, which is scaling data and arrays as a feature. So let's start with the first one and understand what data representation is and what we can do with it. Data representation, which we began discussing in the last video, is the way we prepare and organize the data so it's ready for the model to use. A model won't just take raw input as it is. We need to pre-process the data and extract features from it so it's ready to be fed into the model. This process is known as feature engineering. For example, when a model like a decision tree receives this data, it tries to learn the data representation and the relationship between the features. Let's say, for instance, I'm a program in a ride-sharing app and want to create a model to predict high traffic hours based on time and whether it's a weekend or not. If it's after 4 p.m. and today is a weekend, the trip price might be high. But if it's before 4 p.m. and not a weekend, then the price remains the same. This is a simple example with basic features, but it illustrates how a decision tree could use the features or data representations you've created and apply it. Last time, we discussed that one of the things that you might do while preparing features is scaling. We didn't go over why it's necessary, since we are dealing with numbers anyway. Why should we do anything to them? The answer is that most machine learning models we use have optimizers that work better with numbers in range of -1 to 1, like gradient descent for example. This is because when features have large values, their derivatives also become large, causing unstable updates or very large steps, which means you might need more steps to converge or reach the optimum. The book even conducted a simple test, where it took data with one feature and its label, and gave it to 2 models, one with the data as it is, and the other with scale data. After training both models for a set period, it was found that the model trained on scale data performed 9% better than the one trained with unscaled data, confirming what we just discussed. Another example that highlights the problem is k-means clustering. Since it calculates the distance between points, if one feature has large values while other doesn't, the distance calculation will skew heavily towards the larger feature values. As shown in this example, even though the difference in the first feature is about half of the baseline, 4.5 out of the 9 is half, if we consider the first number to be the baseline, all the outputs are skewed towards the other feature because of its large values, making any contribution from the first feature insignificant. This is despite the fact that ideally, the second feature should have a smaller influence, given it's way closer compared to its values. 179k out of 180k are almost similar. I hope this example makes the problem clearer and helps us understand why scaling is needed before feeding the data into the model. After that, the book begins showing us the different types of scaling, which include both linear and non-linear methods. Starting with linear scaling, we have 4 types. The first one is min-max scaling, also known as normalization. The second one is z-score normalization, often called standardization. The third is clipping, where you multiply your data by a number to create a new range, then trim the extremes, so that any value outside the bounds is brought back within the chosen range, like bringing outliers within a manageable range. The last one is Winsorizing, which operates on percentiles and involves clipping and normalization, where, for example, you take the range between the 10th and 90th percentiles and then normalize them. These are types of linear scaling. As for non-linear scaling, the book mentions 3 types: log, sigmoid, and polynomial expansions. So why might you need non-linear scaling in the first place? The reason is that sometimes the distribution of the data requires adjustments. For instance, if the distribution is heavily skewed in one direction, it makes it more difficult for the model to learn effectively. Ideally, the distribution should be uniform or normally distributed. If the distribution isn't one of these, We can use nonlinear scaling to adjust it to get closer to a uniform or normal distribution. As you can see, the log transformation in the image has shifted the data towards a bell-like or normal distribution, which is what we are after. With that, we have covered scaling and can move to another challenge, arrays as a feature and their various types. For example, let's say you're trying to predict the sales of a new science fiction book, and one feature could be the sales of other books on similar topics. You might have a feature that's a list of values with a different length for each row, representing various sales data for different books of the same topic. When training a model, the model is trained on a fixed number of features and expected the same feature structure for every new prediction. So, how do we solve this issue? There are several ways to handle this when the feature is a numerical list, like in the example we just discussed. One approach is to calculate the statistics for the list, such as average, median, maximum, or minimum, and use those as the model's features instead of the entire list. These statistics capture most of the useful information for the model. Another option is to represent the list with its percentiles. For example, you could have 10 features, each representing a different percentile like the 10th percentile or the 20th percentile and so on, preserving the distribution of the list within those 10 values. Alternatively, you could use the most recent 7 sales records as features for the model and drop any older ones. If there are fewer than 7 values, you can add padding, such as -1, to fill in the missing spots. That's for numerical lists. Can we apply a similar approach to categorical lists? Well, not exactly, because it introduces a challenge we briefly mentioned in the last video. Remember when we said that categorical features can be ordinal or nominal? For ordinal features, we can convert them to numbers, since they have a natural ranking. However, this doesn't work with nominal data, where there is no inherent order. We mentioned then that we would discuss this in more details later, so let's dive into it now. Instead of encoding categories as numbers as shown in the image, where the model might learn that German is better than Chinese because it has a higher value, or English is better than Chinese because it has a lower value, we will use one-hot encoding. In one-hot encoding, we create a feature list with the same length as the number of categories, where each feature represents the presence or absence of a specific category. For instance, in this image, the first feature represents English, the second represents Chinese, and the third represents German. Each of these is either 1 or 0, similar to true or false. This way, there is no implied ranking between categories, only whether a function is present or not. A final note, some may think of using only 2 features considering 00 as German. This is known as dummy encoding, where we drop the last feature because it can be inferred from the others. However, we discussed the scenario where the model might encounter a category it hasn't seen before. To be prepared for this case, we won't use dummy encoding, keeping the last feature available for handling missing values instead. Sometimes, a feature might come in as numeric, but we may want to convert it to categorical and apply one-hot encoding. For example, if we have an age feature, we might categorize it as young, middle-aged, or old, instead of leaving it as a continuous number. Similarly, for days of the week, instead of encoding them as 1 through 7, which suggests ranking, we can use categories like weekend and weekdays. This can make it easier for the model to understand relationships, especially when there are categorical distinctions. For instance, in the real estate context, having a category for old or middle-aged would help the model capture that old buyers may have higher chance of buying the property compared to younger buyers, without trying to fit all ages into one continuum. Fortunately, handling categorical arrays isn't too different from numerical arrays. We can use the first 2 methods mentioned earlier, like calculating statistics such as mod, or using only the last 3 or 5 entries. Additionally, we can look at the count for each category. For example, in the earlier example, we had 2 third categories, 1 first and 1 second. We can add these as a feature, with the number representing the count. Alternatively, instead of row counts, we could use relative frequencies, or the proportion of each category. In that case, since there are 4 entries and 2 of them are third, we would record 50%. These 2 points, the scaling and array as a feature, are the main areas we needed to cover in the introduction to this chapter, as we will need these concepts later for understanding the patterns. To summarize quickly, we discussed three main points: data representation, which we touched on previously, and focused in this video on two key challenges within representing these data: scaling and arrays as a feature. We discussed why scaling is used, the types of scaling, linear and nonlinear, and how to handle features that are arrays, whether they are numerical or categorical. I hope you found this helpful. If you have any questions, feel free to leave them in the comments, and if you have any feedback, please share it as well. I would greatly appreciate it. See you in the next video, inshallah, where we will dive into our first design pattern. Bye bye.